Differential equations 6.1 day 3. We're now in our part 2 of the video. We left off where we noticed we had two power series. Both of them had x to the k once we made a nice substitution, but the first series started at k equals 0. The second one started at k equals 2. We decided to plug in k equals 0 into this first series right here, and we got c sub 2. Then we plugged in k equals 1, and we wound up with 6 c sub 3x. And then what we suggested was just to stop right there, because now once you've plugged in k equals 0 and k equals 1, now you could have something really, really wonderful. You can look at these two series and say not only do they both have x to the k, they both also have the same starting point. So I'm just going to recopy these first two terms, but here's the benefit in what we've just done. Now, rather than write two separate sigmas, two separate power series, we could write just one. And please notice both of these series have x to the k, so I'm going to actually factor x to the k out. And, joining these two things together will be great, because now we're going to be able to take a look at a very important principle. We know on the right-hand side, we have 0. So what's in front of x to the first? Well, a 0. What's in front of x to the second? Well, a 0. What is your constant out in front? Well, a 0. In fact, whatever is in front of any power of x is a 0, and we're going to make use of that fact right now. We're going to say, look, that's true for this constant. 2c sub 2 equals 0. It means that c sub 2 equals 0. Look at this, 6c sub 3 equals 0. Well, you can divide. You will quickly find that c sub 3 equals 0. And it's at this point where we could immediately make a terrible assumption and assume that every coefficient is 0 and we only have a trivial solution. However, the real analysis that you're going to be taking place in is right here. That whole big bracket is equal to 0. And if that's set equal to 0, what we can do is actually solve for c sub k plus 2. And I'm going to do that right here. That means we could subtract c sub k minus 2 and then divide by k plus 2 and k plus 1. And this right here is the critical step that we're going to see over and over again in these series solutions. We're now going to be able to plug in values of k to help us. So, I'm going to plug in. If I plugged in k equals 0, by the way, I already know what c sub 2 is. If I plugged in k equals 1, I already know what c sub 3 is. So instead, I'm going to plug in k equals 2. And that means that 2 plus 2, I'll have c sub 4. And 2 minus 2 is a 0, so I'd have negative c sub 0. And down below, 2 plus 2 is a 4, 2 plus 1 is 3, 4 times 3, you'd get a 12. So we do have a non-zero coefficient here. Take a look at that. We could say, well, what would happen if we had k equals 3? Well, you'd have c sub 5, wouldn't you? And 3 minus 2, well, you'd get a c sub 1. So you'd have a minus c sub 1. But 3 plus 2 in that denominator, first parenthesis is a 5. 3 plus 1 is a 4. 5 times 4, you'll get a 20. And we're going to keep going here. We're going to, continue to work here, but take a look right at this next step. K equals 4. This is kind of interesting. You're going to have C sub 6, and your numerator, 4 minus 2 is a 2, so I'm going to have negative C sub 2. And, of course, down below, 4 plus 2 is 6, and 4 plus 1 is 5. We'd have a 30. But please, please, please remember that C sub 2 is 0. Likewise, C sub 3 is 0. You might guess that that's going to be important in just a moment. So that's a 0 all over 30. Guys, C sub 6 is actually just a 0. Take a look at what happens at K equals 5. You'd get C sub 7, but 5 minus 2 is a 3. We'd get negative C sub 3, and 5 plus 2 is 7, and 5 plus 1 is 6, and 7 times 6 is 42. But here we go again. Look at this. C sub 3, that's a 0. Now you might wonder, well, are we going to have the rest of these always equaling 0? You might guess no. Let's just do maybe a couple more to see the pattern. K equals 6, you'd get C sub 8, right? 6 plus 2. And then 6 minus 2 is a 4, so we'd get negative C sub 4. And down below, 6 plus 2, you'd get an 8, and 6 plus 1 is a 7, and 8 times 7, of course, is 56. But, look, I know what C sub 4 is. It's negative C sub 0 all over 12 all over 56. And guys, right now we could clean this up just a little bit more. 12 times 56, wow, well, look at it this way. 12 is really 4 times 3, isn't it? And what's 56 times 4? Well, 4 times 6 is 24. That's carrying the 2, 224. Multiply that by a 3, and you'd get 672. So just wanted to show you can multiply in clever fashion and, not have to use a calculator. Certainly you have a calculator at your disposal, though. Let's do maybe just this last one. You can see at the top of the screen, we're going to find C sub 9. And that would be negative C sub 5, right? 7 minus 2 is a 5. 7 plus 2 is 9, and 7 plus 1 is 8. 9 times 8 is 72, isn't it? But what is C sub 5? Well, go to the top of your list here, and we worked it out. We'll have this negative. And by the way, you know what? I just realized something. I made a little mistake on the last one because I just noticed something. Please watch out. I forgot to carry over this little negative. I substituted in for C sub 4 up above. I think I got so worked up with the arithmetic of multiplying 12 times 56. A negative times a negative is a positive. You're going to get the same thing happening here when you substitute in for C sub 5. You've got a negative C sub 1 over 20, right? And a negative times a negative is a positive. So, yeah, C sub 8 is positive. C sub 9 is going to be positive. And what is 20 times 72? Well, you just double 72 and you put a 0 after it. Look at that. You get a positive C sub 1 over 1,440. So, right here, we'll take a little bit of a break from generating all this and say, okay, let's just go back to the basics and know this, that our general solution, we really are assuming we have a Maclaurin series, right? And sometimes it's very helpful to just write these all out, and then you can see what's really happening. You can say, wow, I've got all these terms worked out here. We've got C sub 6 x to the 6, C sub 7 x to the 7, C sub 8 x to the 8th, and then even a c sub 9 x to the 9th, and this would of course continue. But guys, look, c sub 2 and c sub 3 were both 0. And I'm just going back to what we saw right here. And we also saw that c sub 6 and c sub 7 were 0. So we're actually losing a number of these terms, and we're losing them pretty quickly. So things are going to clean up pretty fast. So I've got c sub 0 plus c sub 1x. C sub 4, well, you can see at the top of the screen here, negative c naught over 12. So that's where we've got this thing right here, a negative c naught over 12 x to the 4th. You'd say, what about what's in front of c sub 5? Well, a negative c sub 1 over 20. And then we could say, what about c sub 8? Well, we saw that that was a positive c sub 0 over 672. That's this thing right here. And that's going to be what's in front of x to the 8th. And then x to the 9th would have this one, c sub 1 over 1440. X to the 9th. And this can look rather strange. You know, you can look at this and say, wow, I'm not really seeing much of a pattern. I hope you're noticing that what's really occurring is you've got two different constants in place, c sub 0 and c sub 1. Tell you what we could do. I'm going to go ahead and say, let's let c sub 0 equal 1. And c sub 1 equal 1. And a lot of times kids will say, well, can you do that? Well, of course you can. These are just arbitrary constants. You could have billions of answers here. What would happen if that were the case? Everything with a c sub 1 would disappear, and we would be left with a 1. Just look at wherever you have a c sub 0, and you'd have a minus 1/12 x to the 4th. Here you'd have a 1 over 672 x to the 8th, and we can say dot, dot, dot. But look, who says that c sub 0 had to be 1? Maybe you want that to equal 0, and maybe you want c sub 1 to equal 1. Well, then you'd come up with a second solution, wouldn't you? Everywhere where you have c sub 1, just turn that into a 1. Anything with a c sub 0, lose it, drop it. And it doesn't take you too long to see this. And then a pattern, I think, emerges a little bit more nicely. You can see this looks more typical of what you could see. Final answer, you could say, look, I'm going to take a general constant times c sub 1, a general constant times c sub 2, where y sub 1 and y sub 2 are right here. C sub 2 times y sub 2, c sub 1 times y sub 1. That's that theorem that says we should be able to come up with two distinct power series, and we add a linear combination to them. So yeah, when you get this big mess, just make one of the constants disappear at a time, and good things will generally happen. So for our assignment, let's say on page 230, we'll do 27, 29, 31, and 33. Good luck.